catch up.
I picked the wrong part for her.
Are you serious?
Yes.
What happened?
Literally, like, I'm like, I just met with her. And we, like, got it. I
Is
think
she
kind
gonna
of
do
figured
it?
out.
She gonna fix it? I mean, it doesn't matter.
Yeah.
She should fix it, and she's the one that should have done it.
Yeah, she doesn't have class at 11, and so she's working on it right now.
Did she apologize?
No.
She didn't apologize?
No.
Wow.
And then I went and talked to the professor, and I was like,
Okay,
I picked the wrong
the
part for her, and she's like, well,
first
sorry.
description, we have a chair. All the black labels are axial, all the blue labels are equatorial. That will flip into a boat, which also has 6 axial positions and 6 equatorial positions, but different distribution. Okay, I think we're fairly good with that. What we now have to do is start adding complications to the ring, like substituents. Plus,
So the ones that do it kind of.
we have to show that the Newman projections that we learned for just regular sp3 carbons, these are all sp3 carbons, also work. Okay. So, I'm going to put it there. Eyeball. This eyeball is going to look straight down the middle of this molecule. Just putting these in at random today, no color coding. Okay. His chair, back, the seat, the front, sits on 3 axials, 3 axials the other way, and then the equatorials point outwards, they radiate out from that ring. Okay, we are going to look at this molecule this way. And I say oftentimes, this is going to get kind of big and ugly and frightening. And if you're frightened by the molecule that's on your page, just put your thumb over it. So, right now, we're just going to put our thumb over this. But what can you see? Right here, I see the Newman projection that comes to a 3-pointed upside down Y, and there's another Y-shaped projection behind it, which tells me, oh, that's staggered. Okay, so yeah, this big ugly molecule right here that we have to deal with. And then, you know, just coincidentally, there's another one on the other side, and it's staggered also. So all I'm going to do is write a staggered Newman projection down, And then I'm going to write another staggered Newman projection off to its right. And then I'm going to meet them, I'm just going to join them up in the middle. It's not that threatening. I look straight down this molecule. Well, if I'm going to do it this way and be honest to my diagram, this is an axial position right there, and an axial position right there. So the Y shape is sitting on that axial hydrogen like that. This is axial, and axial, and axial, and axial. All the black ones are axial, all the blue ones are equatorial. And I know that blue and black don't really work very well on this board. Okay. That's the front of my molecule. You see those hydrogen to carbon bonds, and then they're staggered. Like that. So let's do it just the way that it's shown on the screen. Here's my carbon at the front. There is an axial bond down to a hydrogen. There is an equatorial bond up. Behind it, there is an axial bond up and an equatorial bond down, which is kind of occluded from view by that circle right there. And then this joins up to the CH2 group right here. What are CH2 groups called?
Okay.
CH3s are methyls, but a CH2 that is in between two other groups is a methylene. This is a methylene right here. Goes up and then comes back down. And now I've got another Newman projection right there. So I'm going to draw the other Newman projection. And my Newman projection looks like that. So I can see the relationship between these groups right here and here, and then just tagged in the middle. There's a couple of methylenes that we just write as condensed structure, CH2. Because if we try and write those out, it's going to get ugly. Okay? Same thing for the boat. So this is a chair with the back, the seat, front. I'm going to turn that into a boat. And a boat now sits on 4 axial groups and has 2 axial groups. We're going to draw them pointing directly up, but they actually lean in a little bit. So this is what a Newman projection of my boat is going to look like. And again, this one might be a bit threatening. So I'm going to put my thumb over half of that molecule. I've got a Newman projection on this side. Here it is. It's coming into that Y right there. And then behind it, there's another Y. So this is now eclipsed. So the boat is eclipsed. And the chair was staggered, so the boat's not getting off to a good start. This one's going to be higher energy in terms of conformation. So I'm going to draw these coming to a point where I can see the Y, and then a circle behind it, and then these bonds radiating out from that. And then on the other side, I'm going to draw just the same thing, with methylenes in the middle. Front of my left-hand side, and then this is going to be eclipsed. So write those bonds as close as you can get to one another that are still legible. One of these bonds manages to get through the circle, and the other one emanates from the circle. Tells me that this bond is at the front, and that bond is at the back. That's eclipsed, and this one is staggered. Chairs are better, lower in energy than boats, because chairs are staggered and boats are eclipsed. It is as simple as that. Okay? So that's the big first ugliness over and done with. We now know all the important stuff about cyclohexanes. There's more than that. There's a thing called a twist boat. It's in the book, you can read it. This is good. That's not good. We're going to spend more time here than there. All right, let's start switching some of these hydrogens out for other groups. So there's a boat in between these two chairs. And we're going to pass through that boat to get to the other chair. And any group that is currently here, when it flips to the other position, will end up there. The axial positions turn into equatorial positions, and equatorial positions turn into axial positions. Now, that's a combination of equilibria. Remember equilibria constants? The equilibrium constant is the concentration of the product divided by the concentration of the reactant. For us, we can write an equilibrium constant that tells us they really should be lowercase. The preference of my group X to be in the equatorial position over the axial position. Okay. Now, when X is hydrogen, the value of K is exactly 1, because there is no preference for hydrogen to be axial or equatorial. It just takes what it gets. There's no preference. But it turns out that being in an axial position is not as fun. Maybe it's more fun. Maybe it's too much fun than the other way. broken. These won't do. Did I break one this week? That looks. Okay. I am missing. I need to super glue. Let's put a methyl on here. I broke this atom, so it's not going to work anymore. Here's a methyl. Look, there's the stupid models. Okay, if, let's put this in a chair. So here's a chair. If the methyl sits in an equatorial position, then it points away from the ring and it points a little bit up here. So its nearest neighbors are right here. That one's there as well. That one points down and outwards. So it's not really lining up with anything. If I flip this to be in the other chair conformation, now its nearest neighbor is right here. See it? This methyl really doesn't want to be here, even though that's a hydrogen. Axial positions are closer to the repulsive electrons in other bonds. So groups other than hydrogen, any group other than hydrogen, is going to want to be in an axial, there's an equatorial position. We can quantify that. When you are a fluorine, homework question. Okay, it's about 1.5. So you're 50% more likely as a fluorine to be in an equatorial position than you are in an axial position. And if you have a molecule that's got 2 of them in it, and you have free reign, you can put them anywhere, put them both equatorial. By the time I make this a bromine, okay, so if this is the size of a carbon, then hydrogens are this big, and hydrogens have a mass of 1. Is there a periodic table in here? Yes, it should be. If that's the size of a carbon, how big is a fluorine? It's bigger because it's got more stuff in it. Because carbon is in position number 6 with an atomic mass of 12. Therefore, carbon has 6 protons, 6 neutrons, 6 electrons. Fluorine's in position 9. And it has 9 protons, 9 electrons, has a mass number of 19, therefore it's got 10 neutrons. It's got more stuff in it, which makes its size be what happens to the atoms as you move across the period? They get smaller. Wait, what? As you move across the period, your atoms get smaller because of that thing, general chemistry. You didn't take general chemistry with me because I hammer this into you. This is effective nuclear charge. If I'm a carbon, 1, 2, 3, 4, 5, 6 protons. Here's an electron. How attracted is that electron to the nucleus? 6. Here's a fluorine. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's an electron floating around it. Is that electron more attracted to the nucleus or less attracted to the nucleus? More attracted to the nucleus than carbon. If it's more attracted, it moves in for a better view. As you move across the periodic table, counterintuitively, because you're stuffing the atoms with more objects, the radius gets smaller. It's called contraction. Across the periodic table, across the period, the atoms contract. So fluorine is not bigger than carbon, but it does weigh more. Gives you a preference of 1.5. Now, do the hand gesture again. Here's a carbon. This big. How big's a bromine? Your hand gesture is now appropriate. Bromines are bloody enormous. Because as you move down the period, as you move down the group into a new period, you enter a new quantum shell. What was the principal quantum number called? N. N is my principal quantum number. We all need to remember our general chemistry. You move into a new shell and your atoms get much, much larger. Bromine's preference is about 3. I think it's 2.8. Be aware that I'm largely making these numbers up. I have no reference. But it's about 3. So it's 3 times more likely to be sitting in an equatorial position than an axial. And how much does bromine weigh? You are allowed to look on the periodic table. It's very heavy. It weighs 80. By the time you're a methyl, I may have to make this number up. I don't remember this number. That's a methyl. How much does a methyl weigh? It's a 12 and 3 ones, so it has a mass of 15. This one's going to be, we'll have to look this number up because I'm wildly guessing at that one. That's about 15. So now we're really off. We have a very, very clear distinction that methyl cyclohexane does not want to do anything other than sit in an equatorial position. By the time you get to be tertiary butyl, oh, here's my group. This is called a T-butyl. We are allowed to give these abbreviations. Methyl is capital M, lowercase e. But that's only 1 pen stroke less than CH3, so we don't use it all the time. But butyl is Bu, and the superscripted T tells us that there are 3 groups in that 4 carbon chain. This is a tertiary butyl. So here's the carbon that I'm bonded to. Trying to make them all about the same size. Bond to another carbon that is then tetrahedrally, running out of space, bonded to another one, which is then tetrahedrally bonded to another one, which is then tetrahedrally bonded It's about size and shape. It's not about mass. Because bromine is heavier than all of these things. Bromine is enormous and has a big mass to it. It's not about mass. It's about bumping into other objects. And a sphere doesn't make as much clanging, banging around as something big and branched and ugly like this. 1,600 times more likely to be found in an equatorial position than an axial position. Okay? So now, when we start thinking about our molecules, we need to think about them as chairs, not boats, and we need to think about our substituents being in equatorial positions. That number's completely made up. I will have to go back and fix that number. I don't remember. But that order of magnitude seems about right. Okay, let's make some pictures. Question. Sketch. Closed. Stable. Confirmation. Methyl cyclohexane. It's easy. Most stable. Means it has to be a chair. Ethyl is going to be at the equatorial position. So sketch a chair. Put the ethyl at an equatorial position. And not one of the ones at the back. Put it at one of the ones at the front where it's obvious that you can see it. Here's the chair. Those are my axial positions. And here are my equatorial positions. And the question didn't say anything at all specific about where it wants it. So I'm going to put it on a place that the reader can see it. It's right there. We'll skip the Newman projections because we're going to do several of these. We'll do the Newman projections on the next round. Here we go. Question. Sketch. Post. Stable. Confirmation. What was your homework question? Because I'm not going to do it on the board. Sketch the most stable conformation of cis 1,2-dimethyl cyclohexane. Okay. Question gives you all the information that you need. Most stable. Going to be there. And these should be equatorial. Cis, of course, means on the same face. Here's the chair. One of these needs to be carbon number 1 and one of them needs to be carbon number 2. Show of hands, who thinks that right there should be carbon number 1? Good. Why should that not be carbon number 1? It's at the back. It's hard to read. Should that be carbon number 1? I have no problem with that being carbon number 1. What about this one? That would be fairly good at being carbon number 1. That's not as good. That would be okay because it would leave that here. So something that pushes away from the ring and is clearly legible, good idea. Something that gets jammed in with all the other stuff at the back, bad idea. I'm going to make this carbon number 1. So a methyl needs to go here. And it needs to be on the same face as the other methyl. Okay, so what I'm going to do first is I'm going to write all the other atom labels in. And then that just leaves me carbon number 1 and carbon number 2. Okay, so carbon number 1 has an axial and an equatorial position. Carbon number 2 has an axial and an equatorial position. Just got to figure out what's what. So that's number 1 and that's number 2. The methyls have to be on the same face. If they're on the same face, can they both be equatorial? Let's go to the model. This is my carbon number 1. That's my carbon number 2. Number 1, number 2. To be cis, my 2 methyls have to be on the same face of this hexagon. So they can both be underneath, or they can both be on top. I'm going to have them be on top. So for carbon number 1 to be on top is here. That's an axial position. To be on top for carbon number 2 is to be equatorial. So there's no way that I can have both groups as cis geometric isomer. There's no way I can split that they're both equatorial. Something has to give, but because both of those groups are the same as each other, I'm just going to split it. Compromise. So that one is axial and that one is equatorial, but they're both on the same face.
So if it didn't say cis, would you want them both equatorial?
Now, if it said, sketch the most stable conformation of 1,2-dimethyl cyclohexane, or the most stable isomer of 1,2-dimethyl cyclohexane, then I would want them both to be equatorial, which means they're not cis. They would be the other isomer called trans. The trans isomer can have them both be in the axial position, or just flip and both be equatorial. When they're both equatorial, one's a little bit up and one's a little bit down. Let's adapt this question. 1, 3, fluoro at the 1, methyl at the 3. Why is my fluoro at the 1 and not at the 3? Why is it not methyl fluoro cyclohexane?
It's alphabetical.
It's alphabetical. There is no rule that says your numbering system has to follow the alphabet, but the fluoro is already there. So 3 fluoro 1 methyl actually follows a trend that's probably more correct, because even though fluoro is lower in the alphabet, the molecule's more interested in the position of branching. So technically, this should go the other way. It should be 3 fluoro 1 methyl. It's a check. Pick out now which atoms you are going to designate as carbon number 1 and carbon number 3. Don't let one of those numbers be at the back of the molecule. So if that's carbon number 1, that would be 2 and 3. So I could have the relationship here. That might be clear, but you know what would be better? 1, 2, 3. That one's got real estate here that I can clearly see if it's equatorial or axial, and this has got real estate out on its own right here. The best place for me is 1, 2, 3, or 1, 2, 3. To my eye, those are the easiest to scan. Okay? Trans means they are on opposing sides, or opposing faces of this hexagon. If that is up, this equatorial position, if this is up, then the other face of it on the 3 position down, equatorial and axial. Again, we've got a mix. Cannot have both of these groups be equatorial, cannot have both of these groups be axial. One or the other. Okay, so I'm going to make one of them be equatorial, and I'm going to make the other one be axial. Which group gets to be equatorial? The methyl does, because of that list that I drew. That's up. This is down. Everything out, all the other labels go in. Once you've figured that out, all the other labels go in. The methyl has a greater preference for the equatorial position than the fluoro does. Okay? Let's do one where they're both the same. Trans, 1,2 dimethyl cyclohexane. identify which carbons are going to be carbon number 1 and carbon number 2. There you go, I'm going to make that number 1 and that number 2. Let's have the methyls be trans to one another. There you go. The methyls are trans to one another. And then you fill in all the blanks and you turn that in as your homework. And hey, you get points for writing the chair. You get points for showing me that they're trans. But boy, is this the wrong answer. Because that's an axial position. And methyls don't want to be in the axial position. They really would prefer, if you could make it happen, to be in the equatorial position. The equatorial positions on those two carbons look like this. One is a little bit up, and one is a little bit down. Does that count as being on different faces? This is an equatorial position. It's pointing upwards. It's on the top face of this hexagon. One position away from it is another equatorial position. It's pointing down. It's on the bottom face. Their relationship is 1 up, 1 down, so this is trans. But they're both equatorial. It's just a little bit up and a little bit down. It doesn't have to be all the way up and all the way down. That would also be trans. But the axials are going to start bumping into these other groups. And they don't like that. This is your answer. Like all the other labels. Okay. Now, in the remaining 4 minutes, draw them all again as Newman projections. They're all chairs, so that's not difficult to do. Which way do we want to do it? So, I'm going to look at this one. I did this because this is where I just finished. I'm going to look at that one first. Do I want to put my eye here and look at this molecule with the methyls at the back? Or do I want them to be up front? Let's have them be up front. I'm going to look at it this way. And when I look at it at the front, those hydrogens, they're axial, they're pointing down. Which means the equatorial positions, hold on a second. No, it's the wrong one. It's the wrong one. My bad. That one's down, and that one's up. So the front of my molecule, which way am I going to look? Oh, you know what? Yeah, okay, hold on. We entered a problem that we hadn't anticipated with running out of time. Because I'll have to write it out for you. I'm going to do it the other way. Because my Newman projection looks like this. Okay? It's a chair, so it's going to be staggered. Because that's the basis of my Newman projection, I cannot see these two groups if I look directly at them. I cannot see that because that methyl would be attached here. And I don't put any detail in this bridge. So what I need to do is have them stacked one behind the other. So I'm actually going to look at the molecule this way. Trust me. Don't do the dumb thing that puts the carbon that you want. So that's going to be number one, and this is going to be number two. Number one is right here at the front, and number two is at the back. Okay? Don't ever put a carbon that you're interested in this middle section. That would be really, really counterproductive. Okay. This is a 1, 3. So I made that 1, 2, and 3. Now these can be on different sides of my Newman projection. Can you see that? 1, 2, 3. Don't ever lull yourself into putting anything where there is a substituent in this middle part of the Newman projection. Think it through. Scribble labels, numbered positions on your molecule, and track them through. Your template for the Newman projection is always going to be the same. I'm very, very rarely going to ask you a boat. It doesn't happen because it's not important. So your template is always this. Figure out your numbered positions. Don't put substituents here. If you put substituents here, you cannot show me if they are axial or equatorial. You cannot show me their relationship. Okay? So if it's a 1, 2, have 1 at the front, 1 at the back. If it's 1, 3, have 1 here and the other one on the other side. Got it? Okay, that homework's due now Friday. Yeah.
Good luck.
So we would have to. Yeah.
I used to like one as an example.
Okay.
Like I just
Methyl.
played, and I said, "You need people." And Dr. Christian, my Sarah, or my partner, who's Sarah, and then I had a picture of Patrick.
So what I've done
And they're like, Michael.
is
Ooh, you got my name wrong. They got the name wrong. It was good. It was
blue on the side.
have fun.
All right. So right now, that's the bottom part. Here's the back of the chair and the seat. I have blue pointing down, blue pointing up.
Yeah.
So this is different faces. This is trans, and 1, 2. Now, in order to show that as a Newman projection, I'm just going to twist my perspective to look at it this way. So you look straight down the middle. That's carbon number 1, carbon number 2. Yeah, I've got my Y here, I've got my Y here, and the CH2 of methylene up top. These meet in the middle. And this is the front of my molecule right here. Yep. And my blue methyl at the front is pointing up. Behind it is a circle that occludes my view, and this blue methyl is pointing down. And then this methylene at the back is pointing down.
Okay, now I see.
Little bit of practice.
Yeah, I was trying to
Just
look
a
at it
little.
this way.
Mhm.
Almost impossible to do
Yeah.
this way, right?
Yeah, don't
Yeah. 'cause
don't
this-
view them
this way
with
here.
the bond of interest
Yeah.
in the middle. Just rotate it one position.
Okay.
Okay? Make this bond that points up and that bond that points down right here. Just have them be regular CH2s.
Okay.
If you do that, mostly everything else falls into place.
Thank you, sir.
I missed lab yesterday for golf tournament.
We also have lab tomorrow at 9.